In this demonstration, we're going to be looking at a piece of tubing that's got some flaws in it and also a dent, so you can see how a dent behaves when you're using multi-frequency impedance plane data analysis. So let me hit Start Acquire. And you can see here's the bobbin calibration standard. It's 1 inch by 0.49. This is 7030 copper nickel. So I have my probe just inside of the standard. I'm going to hit null. I'm going to push the probe out, and then I'm going to slowly pull it back. We got a bunch of signals there. So now I hit Stop Acquire. And this is always how you analyze bobbin data if you're doing it the right way. You do it once the entire tube record has been recorded, so you can take as much sweet time as you need to do a thorough and complete analysis. So what I've done here is I've already rotated my signals. But what I'm going to do is I'm going to position all 4 frequencies kind of on the same vertical position on our screen, and then we can step through the cal standard and see how they rotate with different frequencies. Put that one right about there. I think I need to crank down that span just a tad. Probably the same for 150 kilohertz. Take that down a little bit. So the phase angle of this particular signal, so this is the signal from the 100% through wall hole, so just a single drill hole. And for this size tubing, and for the probe that I'm using, this is not a great signal for 100%er. Normally, you would want a 100% signal to look more symmetrical, like these, but it would be rotated over at about 40 degrees, maybe 35 degrees if you set probe motion horizontal. But just know up front that that is not the kind of signal that you want during an inspection. You would probably ask the operator, are you sure you're using the right cal standard? Is the cal standard damaged? Is there any crud in the hole, conductive crud that's giving us some sort of signal interference? But for the scope of this video, we don't really care. But that's 100. It's about 35 degrees or so. And now what I'm going to do is go to the thing that's next to the 100 hole. So there's a 100% hole right there. And I was pulling the probe through this way. Always record on the pull. The next flaw is the 80% flat bottom hole from the OD. So let's look what happens to that phase. That phase is rotated. It's got more phase lag on every channel. Okay, let's change the position a little bit. Keep them separated. You ever hear that song by The Offspring, Keep Them Separated? That's what we're trying to do with these signals, is keep them separated. So this explanation is very crystal clear. Okay, where are all the buttons? There we go. So that's our 80. Next we go to the 60s. Oh, jeepers. You always got to re-null. Null's your friend. Okay, I can kind of see him a little better. Oh my goodness. I'm going to have to bring this guy back over so we can see him. You think this is bad? Wait till you analyze array probe data. There you're nulling constantly. It's very balance specific analysis. If you don't balance enough and in the right spot with the array probe, you miss flaws. So just because it's array doesn't mean it's easy. doesn't mean it's easy. Analysis is hard, especially when you're doing tubing. All right, so this is the 180, 60, 40. Does that sound right? The 40? I think so. Notice how you got even more phase lag, because the flaw portion of the 40 coming from the OD is farther away from the test coil. That's why I have more phase lag. So you can imagine as you go to the 420s, you're going to have even more phase lag. So now all the frequencies are rotated more clockwise. And then we got a huge signal at the end, and that is a 360 OD 10% groove. Well, why is the signal so big? Well, from your studies, you know that the amplitude of a signal is a product of its length, width, and depth. In other words, the total amount of metal that's missing. Where am I at? Right here. Crank that span down a little bit. And we'll go over here. We'll crank down the volume of channel 7 a tad. See how pretty that looks? That's how the 100%er should look. Except when you set the 100% whole, you set it to 40 degrees on every differential channel. Unless maybe your low frequency channels, you might want to set a tube support ring. But for here, that's how we're going to set it. So just to run through these real quick again. There was our crummy looking 100%er. Low phase. Now, keep in mind that the amplitude and the phase of this particular signal, and this is a tiny, tiny through-wall hole, it's a product of, it's a weighted average of all of the disturbed eddy currents at every depth. So now when we get up to the 80, that's going to be a little farther away from the coil, right, because it's drilled from the OD. Now instead of being at like 30 degrees, it's about 45 degrees or so over here. And let's see. I have an important point to make here, and that is OD flaws will rotate counterclockwise with decreasing test frequency. So what does that mean exactly? I'll show you what it means. I'm going to go in here, and I have to put measure. Somewhere there's a measure button in here. I don't even use the software, but I'm going to figure out where to measure it. We're going to do a volts peak to peak. All right. 57 degrees on the highest frequency. Now, without moving my hand, I said that OD flaws rotate counterclockwise as you decrease the test frequency. So when I move over to the red channel there, that's going to be 100 kilohertz. It should be less than 57 degrees. Voila, it's 53 degrees. Now when we go down to the purple data, it's going to be less than 53, 47 degrees. See how that's rotating counterclockwise with decreasing frequency? That is how you do phase analysis. And if you go to the blue, that's the lowest frequency, 30 kilohertz. Now you're down to 215, which only means that when I calibrated that particular channel, I wasn't paying attention, and I got it upside down. And since I know this phase is going to be less than 60 kilohertz, it's probably going to be somewhere in there. So 57, 53, 47, 34. That's how an OD flaw rotates with decreasing test frequency. Now, let's take a look at the strip charts over here. The strip charts, let's see here, let's maybe null it. Bring it down, center them a little bit. I want you to notice that the strip chart on the left is the vertical component of these signals. So what it means is if you got a signal that's sticking straight up and down on here vertically, it's going to stick out a lot on a vertical strip chart because that's the component that this is highlighting. Now, if you look at the other strip chart, channel 1 horizontal, the biggest deflection is going to be from components that have a lot of horizontal on the lysigue. So what do you think that thing right there is? That's a big kick, and it's horizontal. Well, we haven't covered that yet in these videos, but I don't know if you can see it as I rotate this cal tube back and forth, but what do you see right there? That is Dent from the OD. Now, in your studies, you may come across some literature that says, what type of a signal, when you go 5 frequencies higher and 5 frequency lower, doesn't really rotate much off the horizontal? And as you're going to see in a moment, that's going to be a dent or a reduction in tube diameter. So we'll see if I'm right. I'd be willing to bet that I am, because I've looked at thousands, probably tens of thousands of dents over the last 35 years. And when you cruise up to that indication, you always have to scroll your little cursor here in the direction of probe travel as you're recording. You got the 80% flaw, and then you got this great big horizontal kick right about there. So now what I'm going to do, it gets kind of busy looking at all the frequencies at once. So what I'm going to do is, I'm just going to turn every other channel off. And then we're going to go up here, and we're going to pump down the volume on 150 kilohertz. Let's see here. Now, I'm going to have to open my window a little bit to get the whole signal in there. There we go. Return, drag the cursor. And you know, all the software nowadays, when you're doing production analysis of, you know, hundreds and hundreds of tubes per shift, you got a mouse and it's got 2 or 3 buttons on, a scroll wheel, and trust me, you use all of those different clickers and wheels, because each one of them does a very specific thing. So try to use a touchpad to analyze tubing data. Forget about it. It's not going to happen. It's not going to be very efficient. So again, I'm going to get just on the dent, and it's right there. So let me measure it and see what it comes up with. I'm going to go peak to peak. It's going to be 182 degrees. That's flat. So as I scroll up into this data, it's going to form to the left first on differential. So goes to the left, goes to the right, and then it comes back to null right there. Now let's go see if that rotates counterclockwise with decreasing frequency, like OD flaws do when you have an inside bobbin probe. My guess is it's not going to change much, only because I've seen thousands. Look at that. There's your 80, there's your dent. If you want to measure it, and go peak to peak, 181 degrees on channel 3. Then we'll go over here to channel 5. It spans down a little bit on that one there. There's your 80, and here's your dent again, 182 degrees. What do you think it's going to be on channel 7? 180 degrees. So as we stepped through the frequencies, the dent didn't rotate. It just stayed pretty much flat. Now, if you got a dent that's horizontal and it starts to rotate up as you decrease through the frequencies, we call that a distorted dent with an indication, a possible indication. And that's the case where we would probably go in with an array probe or a rotating probe to get more information on that location. Because some things will rotate up just a tiny bit. You know, every dent's a little bit different. But typically, they're not going to rotate much as you go through the frequencies. So that was today's lesson on phase analysis and looking at a cal tube with a dent in it. Like, comment, subscribe, all that good stuff. Thanks.